Welcome to lecture 37 of Industrial Math and Computation. So in this lecture we will introduce machine learning. So in a way this is a lecture in the very end of a course, but I hope it will become clear that we have been already applying many of the techniques that are used into machine learning in this class. So I will try to attempt what is machine learning. In this lecture, I will distinguish between supervised and unsupervised learning. And we will see two techniques, clustering and dimension reduction. And this lecture will end with the proposal of two topics for projects that involve machine learning. Okay, so what is it? What is machine learning? Here is a first attempt, which is actually not a definition. I took this quote: "There is no clear boundary between statistics and machine learning," from a book that is titled aptly Statistics with Julia. So this is also a computational course in which we use Julia as our programming environment. This is kind of very appropriate, but you can see that we started this course with statistics and probability. This is actually continuing that line. So statistics is fundamental and is one of the paths that take you into machine learning. Okay, so that doesn't help us as far as a precise definition. So in some sense, when one solves problems, one wants not to read an entire book. And especially if machine learning occurs in the last chapter, that's not very encouraging. Can we provide a more self-contained version? And yes, we can. So here I took this from a programming book, so scikit-learn, and it follows. It's a good definition because you can comprehend this definition via knowing the analogy with learning. How do we learn something? Well, we learn from experience by doing, so not by just listening to lectures. We do projects. We have certain performance measures, and we repeat this. We keep on doing homework exercises, projects. We look at the performance, what do we get out of this, and this increases our experience. So that is it. So it is also a very workable definition for learning, but applied here in an abstract setting. So we will see that experience can be replaced by data in the computers world. Tasks, we will see clustering in this lecture and principal component analysis. Regression is another very important task that we have applied throughout this course many times. And the performance measure, we have indeed metrics for measuring. So often optimization is also comes in. Perhaps I will probably have to specify this metrics, and how well can this done with supervised and unsupervised learning. So what is supervised learning? Well, supervised learning is when you get an exercise and there's one and only right answer. So if you like, in this course, these are the exercises. Typically, there's one answer, number that comes out, and we have examples. So exercises and examples are often interchanged. We have inputs and outputs and labels. So often labels are also used for outputs. Then there is the category of unsupervised learning, where the program does not have access to the answers. That is often the most interesting category, and in this course you could say that the learning experience you learn from computer projects. That's the unsupervised learning. Okay, we will see clustering, which is one form of classification. Regression is another one, where we have a clear X and a Y value, if you like, an input and an output. As far as unsupervised learning goes, I mentioned clustering, but perhaps this is probably a very bad terminology. So clustering is actually following in the. So I see now that the examples for unsupervised learning, these are the two techniques that we are using today. Okay, before we dive into the two techniques, let me give two examples. As the end of the semester and the end of the spring, beginning of the summer nears, we may perhaps think about traveling plans. So here is the question: what makes Paris look like Paris? If you look at pictures of a city, how can you recognize the city? So this is an example for supervised learning. Because if you take pictures, unless you didn't, typically you know where you are. So there is a correct answer to this question. So I take this paper because I read this paper. So this is published in the communications of the ACM, the Association of Computing Machinery. In the last lecture, I had a paper in the American Mathematical Monthly. So the communication of the ACM is a little bit similar in the sense to the American Mathematical Monthly, in the sense that it is intended for a very wide range of professionals. So the American Mathematical Monthly would go to the professional mathematics educators. The communication of the ACM is sent to all the members of the ACM. So I remember reading this paper, so it is 2015, but when I had to prepare for this lecture, I still remembered this as a very nice paper. So feature selection is also a little bit of prescribing, a retranslating of the title of this slide here. Here it is. So what is the distinction between the two cities? So we have two pictures. One comes from Paris and the other comes from London. So when you think about the question, what makes Paris look Paris, you would think about the Eiffel Tower, but there are not too many Eiffel Towers around, and if you were to look into Paris, you may never see it, essentially, except, of course, if you are a tourist, you see it. But I don't think that's kind of too, not, in some sense, it is representative as a tourist, the Eiffel Tower, but it's probably not characteristic for what makes it typical Paris. Also the same for London. So I won't keep you up into suspense, because if you have visited either city, you know that the top is Paris and the bottom is London. The question is, how can we get this? These are pictures that come from Google Street View. So we can, thanks to Google Street View, we can all visit any city we like. Okay, so here is another example of unsupervised learning. So what is the value of a house? Now, if it is your home, it's probably priceless. But we asking this question here from an economical perspective. So the value of the house is the sales price. And the sales price, we know it at one particular moment in time. But if a house is not on the market, you can't actually really know this. So then there is actually no right answer available. So it doesn't simply not exist. Only when the house is sold, only at that moment, you will know what is the value of the house in the strictly economical sense. So this is an example of the unsupervised learning, and also where prediction comes in. Um, and here you can see where the classification comes in, and the clustering. So how does this happen? How do people set the housing price? Well, you have a professional come in and compare your house, the size of your house, with recently sold houses in the neighborhood. Again, can you have an algorithm doing that? Okay, clustering is one of the techniques. And we will look at a classical example widely known in the pattern recognition literature. So it's a historical example. So pattern recognition is another word you could use. And this comes in biology. How is it that, for example, if you walk, a trained biologist will immediately recognize a certain type of flower? Can you train an algorithm to do that too? So there is the iris plants data. You find it in the R data set, and you also find it in the machine learning packages such as scikit-learn. So it is, in some sense, from a computer science perspective, it is a classical benchmark. Okay, so we will use it, and we will use it from within Julia. So it's a historical data set. So we have certainly heard about big data. Here we actually look at what is in current standards ridiculously small sample set. So we have 150 instances. And these are 50 instances of three flowers. They're called Setosa, versicolor, and virginica. So the instance, it's not entirely trivial. Every instance is actually a vector of length 4, sepal and petal length and width. So for every instance of a type of flower, you have these measurements. So we can think of these things as input and outputs. In a case of supervised learning, so this is an example of supervised learning, where actually we know for all these 4 measurements what is the name of the plant. So we have the features. The features from the full data set are actually now the 4 by 150 floating point matrix. And we have the names. We have 150 strings. So we can see this as input and output. Again, for every... So the question that we actually are asking here is, are these instances, so what we measured from these flowers, are they actually representative, characteristic for the flowers? So just to know what we are talking about here. So what is a petal, what is a sepal? It doesn't matter for the content of the lecture, but here is an image that I took from the web, and you could say this is highly reductive. So we are going to reduce a flower to 2 to 4 measurements: the width and the length of the petal and the sepal. Okay. How do we do this in Julia? So there is the ML datasets, where we get the features. So the features is, if you like, a method that returns an object. In the lingo of computer science, it returns this matrix, the feature matrix, a 4 by 150 matrix. And then there are the labels. The 150 element vector of type string, and you will see everything is neatly organized. So there are 50 all of the same flower, then the next 50 are of the next flower, and then the last 50 are of the third type of flower. Okay, so what do we do with this? So we pretend that actually we do not know the names of the flowers. We only know the four characteristics, the 4 measurements. Okay, so here is a first algorithm. We're going to cluster, so we're going to try with every, so here is a geometric idea. So that's actually what it is. So we also can get into computational geometry. So this is a very basic algorithm. The upshot of that, the alternative is that it's we have to start from somewhere. So notice also the first 2 exercises. So what do? We have our data set. So here we have the 4-dimensional data set. We expect 3 types of flowers. So K is the critical parameter here. So if you do not know K, that's a problem. So the critical knowledge is here, the letter K, the number of centers. And we're going to classify the points in the list of points according to the proximity to any of the 3 if k equals 3 in our application, or if k is any number. So each time, so it's a dynamic algorithm, we recompute the centers, the centroids. It's a multidimensional space. We compute the centroids of the clusters. And we continue doing that until all the clusters are stable. So in some sense, we do not need to consider the entire data set to figure out what are the centroids. So this is an algorithm in pseudocode. Julia is a very powerful language with a lot of features. So the purpose of this exercise, this first exercise, is that you get to try to see if you understand the pseudocode, try to see if you understand the algorithm. The other important point is that, and that's the second exercise, so this is a quadratic time algorithm. So you have the 2 loops. If you have taken a course in algorithms, then you might be a little bit concerned to use this algorithm on huge data sets. But it will only be applied to a limited set. So once you have found the centroids, then actually you can classify in a linear time. Okay, so exercise 1 is important to gain more experience and expertise with programming and Julia in general. But in some sense, in this course, we are solving problems, and what is most important is that we can understand what it is that we are really doing here. So come back to the iris plants data. So two statements essentially, using clustering and then the k-means. Note that we have already extracted the features, the feature matrix, the capital F. So dump is interesting because with dump you can see all the fields in the output. So you will see that there is a counts. I told you before that this data set is neatly partitioned. So 150 columns, and we have three names. So here the names are replaced by integers 1, 2, 3. You see that there are 50 that were quite nicely classified. And then the other classification was actually not, clustering was not done that well. So you can think that this is an algorithm that is not really that good, but I will try to also explain something that you could look at the data, this thing otherwise. Looking at these flowers in a very reductive way, only with 4 measurements, may not be sufficient to make a correct distinction. That could be another point. Now, I ran this algorithm in preparing twice. I ran it once in my favorite terminal way of working, and I once ran it in the Jupyter notebook. And there is a randomization step here at the very initial step. So it depends which 3 data points that you pick. So if you take them all in the first part of this data set, then they all belong to the same plants. And it might be interesting also to study this algorithm. If you do that, what actually is happening. So that's the virtue of writing your own program. So you can actually see what this clustering algorithm does, what this k-means algorithm does on this example set. Okay. We can make a plot. So we have the sepal data, the length and the width. And here is the scatter plot, where you can see how the data is kind of partitioned. The coloring of the dots corresponds to the classification, to the computed classification. So there kind of are the 3 different types of plots, and I probably have to look now a little bit. So the red ones are over here, the yellow ones, and then you have the more purple ones. So this is if we look at the computed assignments in the first 2 dimensions. We can also make the plot differently. So if you look at the petal data, so you see then that the separation is a little bit neater. So you have here one cluster, one clearly distinguished cluster. And I will not drag you to really counting those dots. So should be one group is 50, one is 62, the other one is 30. But you can kind of see that there might be an explanation why the clustering doesn't always match what we know. Okay, so I'm almost halfway. So let me look now at the other technique. We were looking at a 4-dimensional data set. This is in some sense in current capabilities of computers and software. The 4x150 is a toy example, but still we are limited in 3 dimensions. Can we reduce the dimension and extract something from that? And here is what is called principal component analysis. So we start from a higher dimensional space, the higher dimensional data space, and we will project onto we will project the observations, so what we have measured, onto linearly uncorrelated variables. So these are the principal components. So when we do this principal component analysis, we will project onto a lower dimensional space. And then from that we can reconstruct the observations. So the principal components you can see are kind of a projection of the data, and you can reconstruct the data. So there is the transformation and the reconstruction stage. So I kind of indicated in the beginning that machine learning is an extension from statistics. And this is very obvious in Julia. So there is the principal component analysis available in the package multivariate stats. So we had clustering, that was a separate package. Here we have multivariate stats for the principal component analysis. But in the end, everything is always numerical analysis. So this slide is actually intended to remind you to that. So 472 follows 471. Where we considered the eigenvalue and eigenvector computation, so it is reduced to an eigenvalue eigenvector computation. And in some sense, this might scare us a little bit more because now we are typically thinking about algorithms that are cubic in the dimension. But don't worry, we only need not all the eigenvalues and eigenvectors. We only need the principal components. And for that, if you remember, we've seen the power method and also the QR algorithm that is computing the first p eigenvectors and eigenvalues. So the QR algorithm can be seen as a generalization of the power method. Okay, so but it is statistics. So what often happens with data is that so in numerical analysis, we would say that most given data sets are often given as ill-conditioned matrices. So we have huge numbers sitting in there and small numbers sitting in there. Statisticians will standardize the data, so you will compute for every component, for every coordinate that you have, you will compute the mean and the standard deviation. And then one sets up the covariance matrix, which is a symmetric positive definite matrix. So we do two things. So we make the numbers all look of the same size and the magnitude, and then also we turn the matrix into actually quite a nice matrix, a symmetric positive definite matrix. Okay, when we compute the eigenvectors and the eigenvalues, if we compute all of them, we sort them in the increasing magnitude of the eigenvalues. So the power method will actually repeatedly do matrix vector products, and that's again quadratic in the dimension, and that will give us the dominant eigenvector. In this language here, the principal component. Okay, this slide is scary, but in some sense not scary. So we had the F matrix, so the features, the 4 by 150 matrix, and we're going to reduce this to a three-dimensional problem because we want to see the points now. And that's just one instruction. So in some sense, forget about all these eigenvalues, eigenvectors here. I'm just indicating that it still comes here. And you actually see, if I interpret this now correctly, you can kind of see how the significance of the eigenvalues is actually measured. So this computation, it follows also a little bit the power law in statistics, where you see that the next dominant, or the second eigenvalue is not so dominant anymore. All right, so we have this matrix P, which is actually now called the pattern matrix, also called the feature vector. What can we do with this? Well, we can transform the data with this projection matrix. We can transform the data. So it's a 4x3 matrix. So you cannot directly multiply a 4x3 matrix by a 4x150 data set. That's why we take the transpose of this projection matrix, 3x4x4x150, and then we do have a 3x150 data set. So we plot, so we select the first coordinate, the second coordinate, the third coordinate of this now 3-row matrix. We select the first 50 that belongs all to the same class, so the same flower. Then we have the next 50 and then the last 50. And that gives us the three-dimensional representation of the data. And that could explain why in our clustering algorithm it was kind of hard sometimes to distinguish between two types. So one can say it could also be that the features, the feature vector, you actually need all the data also. So when you do project onto 3 dimensions, you can kind of see that these observations, they kind of intermingle. So there's not a sharp distinction between the two. Okay, so training and testing. So we are kind of commingling here supervised and unsupervised. So we have actually a supervised data set. So we have a data set where we know the correct answers. So how can we use this to train a model? We take a subset of the data. So in a way, you could regard the clustering approach, so the k-means algorithm, as an algorithm that does this as well. But here I'm going to try to explain in one slide how you can use this PCA model. So what we do is we take one part of the data set to train the model, and then we test how good the model is on the other part of the data set. So often the first prerequisite for making your machine learning work is, have you enough data? So this supervised setting is actually a very good way to check this. So the question here could be, of this 150 observations, how many would you really need in your model to correctly determine the type of each flower from the model? So here is a suggestion, and I will suggest this as an exercise. So take the odd indexed features. So that means that from the matrix capital F, you select all the odd columns. So there is a nice way to do this with a slicing in Julia. That will be your training. So you will train and then you will reconstruct. So you will transform the features and then you will reconstruct the observations from this. So the iris, so I would say that if you need a hint for the exercise, well, look into the documentation for multivariate stats. So in preparing for this lecture, I got a little tired and I could have done this myself quite easily by reading the documentation a little bit longer, but this is the exercise for you. Look into the documentation of multivariate stats and you will see the answer. Okay, I'm in close to the end of this lecture, so I have 2 more slides to present. So in this course, we learn by doing, so we are doing projects. So this project is a software study. I learned a lot from scikit-learn. So as a computer scientist, this mastering machine learning was a very good introduction to scikit-learn. So I didn't take the statistics route. So here is then a proposal for a topic of a project. So scikit-learn has the nice virtue that it bundles a lot of things. So in some sense, one can regard software also as a library of ideas. And it also what makes the Python as a language, as a computational ecosystem, still very worthwhile. So the step 1 is actually a reading, so don't go too far in there. So I would suggest that we have seen the iris dataset. We have seen how to do with clustering in the Julia package and the multivariate stats to do the principal component analysis. Look how this is done in scikit-learn. So if you need a focus, reading the book, reading an entire book might keep you too long busy. Look at the 2 problems that we looked at and see how to do it there. What are the dependencies of scikit-learn? So that's another way to phrase the second question. And then one example is the Boston housing dataset. So at the beginning of this lecture, what makes Paris look like Paris? The critical point and the main difficulty where statistics also comes in, how do you extract the critical features? So what determines the price of a house? Can you reduce it, say, to the number of bedrooms? Can you reduce it to the neighborhood? So that's kind of the usefulness and also kind of indicating again the difficulty of the machine learning, of a good use of machine learning. So look at the housing price. And regression will again come in there. So we have seen regression throughout this course, and that's one of the tasks in machine learning that is done over and over again. Okay, so here is another project. And by the way, the paper that is suggested here, what makes Paris look like Paris, is very accessible. So even if you are not interested in doing any of these projects, you would still have a benefit, and even not all the exercise, any of the exercises, you would have a benefit of actually reading that paper. It looks very attractive. So there is the computational geocultural modeling. So what the authors did, so I just gave snapshots London versus Paris, but they did a lot more studies, 12 cities. And you can do this thanks to Google Street View. You can all do this from within the comfort of your house or wherever you are. So what is the proposal for a topic of a project? Um, from every city, what are actually the distinguished properties? What makes now Paris look like Paris? But it's also kind of saying what makes Paris Paris. I won't fabricate too much here. Please read the paper and write a summary. Um, to not to trivialize, so this was a paper with many authors, with a lot of work. Uh, it's another way, an entrance into what are actually the key algorithms that you need in such a project. And then one can, so it's always important to read and to study and to learn like this, but you can also learn by doing. And here is a concrete data project. Uh, Take pictures or actually gather pictures. Google Street View will help you from downtown Chicago and the suburbs. And you may also perhaps contrast. UIC has the brutalism architecture. So there is also the feature selection from images. So we discussed this already. I used our office building to extract the edges. So if you look at a picture, you see pixels. In some sense, you can see this as a matrix and just then brutally linearize it. But you can also get the features from the edges. So if you looked at our office buildings or any buildings on the UIC campus in the brutalism style, you might think that you may find a city in the former Soviet Union where the buildings were all like that. So you can perhaps our campus would be a nice fit into the former Soviet Union. Um, so I probably talk too much now. I'm into 40 minutes. So I hope that this lecture was interesting, and this is already project number 20. So these are 20 topics for a final project in 2 weeks from now at the end of this course. So thank you for watching through this. I hope this was interesting.